In this video, we will present our work when epipolar constraint meets non-local operators in multi-view stereo. Given a reference image, a set of nearby source images, and camera parameters, learning-based multi-view stereo (MBS) aims to predict the depth map of the reference image through a deep learning network. Learning-based MBS method heavily relies on feature matching, which requires distinctive and descriptive representations. An effective solution is to apply non-local feature aggregation. Trans-MBSNet is the first method to introduce the transformer into MBS. It has achieved significant improvements by leveraging transformers' global context awareness capabilities. Albeit useful, these techniques introduce heavy computation overheads for MBS. Each pixel densely attends to the whole image. In this case, distractive or irrelevant features can also be attended which are harmful to the feature matching. This raises a fundamental question: where and how to mine non-local context for MBS? Inspired by the classic epipolar geometry, we propose to constrain the non-local feature aggregation within the epipolar lines. Each point only attends the corresponding pair of epipolar lines. In this work, we aim to answer the question where and how to mine non-local context for MBS. As for where, we propose an epipolar line feature aggregation strategy for the representation learning of MBS. As for how, we devise an optimized epipolar pair search algorithm and an epipolar transformer to enable non-local feature augmentation on epipolar lines. Next, we will introduce our epipolar pair search algorithm. First, we introduce some preliminary knowledge of epipolar geometry. Epipolar geometry is a commonly used geometric constraint in stereo matching. According to the theory of epipolar geometry, we summarize the following 3 points. A pixel with a given depth in the reference image can be projected to a pixel in the source image through the homography transformation, termed point-to-point. A pixel with different depth hypotheses in the reference image can be projected to the same epipolar line in the source image, termed point-to-line. The plane that passes through two camera centers and a three-dimensional point produces an epipolar line when intersecting with an image plane. The two epipolar lines of two images form an epipolar line pair, termed line-to-line. Next, we're going to do some mathematical reasoning. Homography transformation allows for point-to-point projection between two images, and we have extended it to establish correspondences between points and epipolar lines. That is, given a point, we can compute the expression of the corresponding epipolar line in another image. Furthermore, based on the theory that epipolar lines occur in pairs in epipolar geometry, we have designed an algorithm to perform the search and matching of epipolar lines between the two images. Here, we showcase the effectiveness of our epipolar line search algorithm. The same color represents corresponding pairs of epipolar lines. Next, we will introduce the epipolar transformer structure that we have designed. Based on the epipolar line pairs obtained from the algorithm, we sample the feature maps and assemble them into a sequence format, representing the epipolar line pairs. We achieve intra-epipolar and cross-epipolar feature aggregation using self-attention and cross-attention mechanisms, respectively, and use additional convolutional layers to re-aggregate local contexts, to fill feature holes and smooth enhanced features. This is our overall framework. We apply the epipolar transformer, ET, to common learning-based MBS frameworks by integrating it into the FPN. Firstly, the epipolar pairs are searched via our algorithm and the epipolar feature sequences are obtained by sampling the coarsest feature map of the FPN. The sequence is then fed into the intra-epipolar augmentation IA and cross-epipolar augmentation CEA blocks. The resulting sequences are mapped back to a feature map, followed by the local augmentation LA module to smooth the enhanced feature map. Finally, the enhanced feature map is sent to the upsampling layers of the FPN, followed by cost-volume construction and regularization. Next, we will introduce the experimental section. In the experiments comparing with state-of-the-art SOTA methods, our approach achieved the best performance on both the DTU dataset and the tanks and temple benchmark. Here, we present qualitative results on DTU datasets and tanks and temples benchmarks. Our method can reconstruct more detailed point clouds in challenging areas, such as weakly textured surfaces. The ablation experiments demonstrated the effectiveness of each component in our module. Additionally, we discussed the design of the epipolar line search algorithm, and our line-to-line approach outperformed in terms of computational complexity and inference time. In comparison experiments with different feature aggregation methods, our method performs best, and we also provide visualization of attention maps. Given a query point on an epipolar line of the source image, ET focuses on the region of its corresponding epipolar line while FMT considers the whole reference image. Our proposed epipolar transformer ET can serve as a plug-and-play module integrated into common learning-based MBS frameworks. We apply ET to another representative baseline CAS MVS net and achieve a significant improvement. Thanks for watching.